Our next topic is finding the correlation coefficient, which is depicted by the letter R. The correlation coefficient R measures the strength and the direction of the linear relationship between two variables. So this coefficient is a quantification. It quantifies about the significance of the relationship. The correlation coefficient R is calculated by a mathematical formula which precisely reads as the deviation of a data x from the mean multiplied by the corresponding deviation of the corresponding data y from the mean and adding them up over the scope of all the datas divided by sample size minus 1 times standard deviation of the x variables multiplied by standard deviation of the y variables. As you possibly already have imagined, this is a very critical formula when it comes to remembering the formula. In our course, we will not stress on remembering the formula or using this formula to find the correlation coefficient. The calculation formula, or the formula that generally will be used to find a correlation coefficient, is given by this. This formula says, in order to calculate the correlation coefficient, you multiply each x data by the corresponding y data and then subtract the sum of all the x data multiplied by the sum of all y data divided by the sample size. And finally, you divide that quantity by the square root of the sum of the square of each x data minus the sum of all x data squared divided by n, and one other square root quantity should be in the denominator, and that will be similar. It will be the sum of the square of all the y data minus the sum of all the y data squared by the sample size. Again, this formula is going to be hard for us to remember. So what we will do in order to avoid using this formula to calculate correlation coefficient, we are going to use Excel spreadsheets. All the Excel spreadsheets are available in shared class file. The Excel spreadsheet that we are going to use for our class today is going to be called the correlation Excel spreadsheet. So I'm going to open that for future problems and finding correlation coefficient, and I will show you how to use that when time comes. So let's concentrate on the lecture notes. There are certain facts that we would like to know about the correlation coefficient. The correlation coefficient R is always going to take a value between -1 and 1. Your values can be equal to -1 and 1, but cannot be greater than 1 or less than -1. When R is equal to 1, we say there is a perfect positive relationship between x and y. The values of R near 1 indicate a positive relationship between x and y. The closer R gets to 1, the stronger the relationship. The variables are said to be positively correlated, and we will interpret that as x increases, y will also increase. Whereas, if the correlation coefficient value is a -1, then we say there is a perfect negative relationship between the variables x and y. Values of R near -1, so that must be a typo, it should be a -1. Near -1 indicate a negative relationship between x and y variables. The closer R gets to -1, the stronger negative relationship there is. So again, I think this is a typo. So both of these ones should be -1. Let me fix it. So -1, -1. The variables in a negative relationship are called negatively correlated. As x increases, y tends to decrease. when the values of r near 0 indicate the fact that there is no apparent relationship between x and y. The closer r gets to 0, the weaker the evidence of linear relationship. The variables are not linearly correlated in this situation, and we can say a non-linear relationship might exist, because in this situation we get two things: either there is no relationship or there is a non-linear relationship. But at least we can say that there is no linear relationship. After we have found out the correlation coefficient, we will do a deterministic test in order to understand whether this found correlation coefficient has any significance in the study of relationship. And the process is described here. The process is pretty simple. It says, first, when you found the correlation coefficient value, you are going to find the absolute value of this thing. Remember, absolute value is going to help you get only the positive portion of the number. So for example, say my r is equal to negative 0.2161. If I do the absolute value of r, I'm going to get absolute value of negative 0.2161, and that will indeed become 0.2161. So that's your step number 1. Then we are going to look for the G table in the table folder in shared class file. The G table consists of sample sizes versus a critical check number. So let me go to the G table and show you how to read that table. So I will just click on the table folder and you will see the G correlation critical check table. Open that. The left column here talks about the sample size of the distribution, and the right column is the corresponding critical check number. So what we will do now? The process describes that if the absolute value of r is greater than the critical value that you have found, then we get to say there is linear correlation. If r is greater than 0, we get to say the variables are positively correlated. If r is less than 0, we say the variables are negative correlated. If r is not greater than the found critical value from the G table, then we will say the x and y variable are not linearly correlated. So in both instances, when you are checking the deterministic behavior of the correlation, you are going to find the absolute value of the correlation coefficient. So I should say that these are absolute values. If the absolute value of the correlation coefficient is greater than the critical check value you found for the problem, then the variables are related. Depending on the sign, if r is positive, you get to say there is a positive relationship. If r is negative, you get to say there is a negative relationship. Whereas if the absolute value of the correlation coefficient is smaller than the critical check value, then we will say there is no relationship between the variables. So this pretty much has described the entire process of finding and interpreting properly the meaning of correlation coefficient. Our next few slides are going to talk about the exercises of this theoretical aspect. So let's go to the next page. This example is referring to a scatter plot, which is a scatter plot of batting average against player's age. So the x-axis represents the batter's age, whereas the y-axis represents the batting average. Question is the correlation coefficient positive, negative, or near 0? The estimated value of r for this data set will be interpreted. So first and foremost, see the pattern of these scatter of points doesn't show you any particular tendency. It doesn't show you any particular shape. It doesn't show you whether the scatter plot is going up as we are going on the edge axis from left to right, or it is falling down. So what I get to say that there is no apparent relationship, hence the correlation coefficient must be near 0. So I'm going to answer this question. I will say that since the scatter plot does not show any particular linear pattern, there is no apparent relationship and if you are careful, you would probably throw in the word linear there. So relationship, but I'm saying there is no apparent linear relationship between, and instead of saying the x and y variable, I will be a little careful and I will say between the edges of the batter and the batting average. So this has talked about the interpretation of the correlation coefficient, whereas to answer the first question, I'm going to say the correlation coefficient must be near 0. We cannot talk about strong positivity, strong negativity. We can say that the correlation coefficient must be near 0. In the next example, I have 3 graphs. We're going to characterize the relationship between x and y, state what happens to the values of y when the values of x increases. This is very important for us to practice this type of problems because this last statement, state what happens for increment in x to the values of y, is the interpretation of a correlation coefficient. So if you look at the leftmost graph, you see a perfect straight line. What does that remind you? So there must be a perfect positive relationship between the x values and y values. How do I know it's a positive relationship? See, as I approach from left to right on the x-axis, the graph is going up. So it's a positive relationship. I would say that. I would say first, characterize the relationship. I would say perfect positive relation. And then I'm going to answer the next question, which is asking me, state what happens to the values of y when values of x are increasing. As I said, this is the interpretation of correlation coefficient. So we'll say, as x values are increasing, y values will increase as well. Now we will concentrate on the second graph. The second graph, of course, is not a perfect rising straight line, but I see a strip of points that is rising as well. So we'll say that this is a very positive relationship, a very strongly positive relationship. So what I'm going to say? I'm going to say that strong positive relation. So this one is not perfect, but it's a strong positive relation. And what happens to the values of y? Well, it's the same thing. We will say as x values are increasing, y values will increase as well. So instead of writing that, I'm just going to say that it's detailed. So we'll say do. The third situation, I still see a strip of points. So if it helps, I will just kind of show you the pattern. It is still a strip of points which is increasing as we are increasing the values of x or y values are increasing. So it's a positive relationship, but not as strong. So the word we're going to generally use to describe a relationship that way, we will say somewhat positive relationship. So this is the word for weak positive relationships. So we'll say somewhat positive relation. But the interpretation of this correlation does not change. It still talks about x values increasing, affecting in y values increment. So it's the same situation as the earlier two cases, and I would answer it similarly. Let's carry on. So our next three examples, if you look at all three of these graphs, they're all falling down. So I know that as x values are increasing, y values are decreasing. But we are interested in understanding which one is strong, which one is weak. So see the leftmost graph, it's a perfect straight line. So as usual, I will say this is a perfect, but this time it should be a negative relation. The second one is a pretty tight form of falling stream of points. So it's a strong negative relationship. So I will say strong negative relation. And the final one, it's still falling down. It's a stream of points that has the tendency of falling down. With the increment of x's, the y values are decreasing. But this is not as strong. So we are going to use the word somewhat negative relation. And I have been skipping writing the interpretation for each of these cases, and because I know all of them are going to be the same, I will write it once, and I will say that as x values are increasing, y values are decreasing. What I would like you to remember, because this is a common mistake done by students, never use a phrase like as x values are decreasing. When you are interpreting correlation, you should always say what happens to y when x values are increasing. Let's carry on. Our next graph is showing us no apparent pattern. It's not quite rising up, not quite falling down. So I get to say that this one is no apparent relationship which means the correlation coefficient is near 0. And finally, we will talk about what happens with the values of x increasing in the increment or decrement of y. Well, there is no pattern, so what I get to say, as x values are increasing, y values do not show any particular linear pattern. And that should take care of this example. There is no particular linear pattern in this situation, so we will say no apparent relationship. Our last example is a graph that again looks like a nice shape, and as I had mentioned earlier, this is the shape of a parabola, and we call this situation non-linear relationship. So we'll say that non-linear, this is clearly not a straight line, because first you have falling down, then you have increment, so non-linear relationship, as the relationship cannot be depicted by a straight line. And in this situation, we will not be able to say in one line what happens to the y values as x values are increasing. So we'll skip the interpretation for the last example. As I have mentioned, for the first half of this graph, as x values are increasing, for example, this portion, as x values are increasing, your y values are kind of falling down. But since then, till the end, as x values are increasing, your y values are going up. So I cannot express that in one line, and it will not be required for us to do. So it is a nonlinear relationship, and we are not going to interpret it in the way we interpret positive or negative linear relationship.